Greetings, AP Statistics. This is Chapter 7, Linear Regression. This is among the longer chapters in the book. Let's get started. So here we have a scatter plot, and it's on roller coaster data. We're going to be seeing roller coasters a lot in this section, as you may have guessed. The scatter plot to the right shows the heights and top speeds of roller coasters in the U.S. And as you could imagine, it seems the higher up the highest part of the roller coaster is, the faster the roller coaster goes. That's how gravity works generally. The correlation between the variable's speed and height is strong. That correlation coefficient R is 0.814. That's a pretty good correlation for real-world data. So perhaps there is a linear model we can make to understand the relationship between the variables. The correlation coefficient R is a measurement of how reasonable a linear model would be to describe data. So if your value for R is 0.814, there's a good chance you can fit a line to those data. First, we're going to talk about residuals. Before we get to talking about a line of best fit, we're going to talk about the concept of a residual. That's going to come up a lot in this section. Once we plot a linear model, so supposing we did, for each x value in the data set, the displacement between the predicted y value, that's called a y hat, all right, that character is, and its actual y value is called the residual, okay? The displacement between the predicted y value and the actual y value is the residual, okay? The linear model should always seek to minimize the residuals, and the residuals are always calculated y minus y hat, okay? So notice there's no absolute value in this expression. This is a displacement, not a distance. This can be positive or negative. For a properly computed regression line, the mean of the residuals is 0. Think about it. If you have a good regression line, you're going to have the same total distance, or rather displacement, of these values above the regression line as you do the displacement of the values below the regression line. Okay, this is all going to be positive displacement. This is going to be negative displacement, but it should be neutral once you add them all together, which would explain why the mean of the residuals is 0. The mean, you add up the data values and divide by the number of values. If you add all the positive residuals and negative residuals for all of your points, you should get 0. All right, so the mean is going to be 0. So here's an example. Suppose the linear model predicts, as this one seems to, that a 77-foot tall roller coaster, so about this tall, has a top speed of 45 miles per hour rather. So about 45 miles an hour right there. Okay? A data point of a 77-foot tall roller coaster had a top speed of 40 miles an hour, talking about this point right here. Find the residual. Well, we got to look at the y values here, and those are speeds in this context. The value for y is going to be 40. That's the actual data value. And this 45 here is the predicted y value. It's what the line of best fit, this green line here, predicts is the top speed for a roller coaster of that height. Okay, so it's the actual data point minus what the line of best fit predicts the y value should be. So the residual would be 40 minus 45 is equal to -5. So our residual would be -5, and should not surprise us that we get a negative number. Residuals are displacements, they're not distances. So now, with a knowledge of residuals, we are going to build a line of best fit, or at least learn how to. And that line of best fit is called the LSRL, which stands for Least Squares Regression Line. So we start out with a little bit of a problem. Our first instinct might be, okay, well, let's find a line that makes the mean of our residuals 0. Well, it's not that simple. Simply adding up all the residuals for each data point relative to a possible line of best fit would make positive residuals cancel negative ones. So that would not be convenient if we want to find the best model. Well, what do I mean by that? Well, you could probably imagine that I could draw a line that's diagonal like this, and I could draw such a line that the residuals on the left of the line, the lower residuals, would cancel out the higher residuals over here. But a line that looks like this would not divide the data up in a way that represents the flow of the data. Our data are obviously up and to the right. So we want a line that's also going up and to the right. So we can't just say, okay, let's make the mean of the residuals 0. There are many ways I could do that. Almost all of them will not actually properly express the data. So we need to be a little more creative. We need to think outside the box, or should I say the square. If we square each of the residuals before adding them up, they all become positive. As long as you are dealing with a non-zero residual, if you square it, it becomes positive. And that makes finding the best model easier. Well, why does this work so well? Well, think about it. The line that makes the residuals collectively as small as possible. That's what we want in a line of best fit. We want to make the residuals collectively as small as possible. That line would also make the squares of the residuals collectively as small as possible. So, in other words, if I were to treat all the residuals like distances instead of displacements, I want the collective distance between each of these data points and the regression line to be at a minimum. But wouldn't the line that does that also be the line that makes the squares of each of the distances collectively as small as possible? That's the power of what we're doing, okay? So the best linear model for statisticians is called the least squares regression line. We square the residuals to make them positive. That's just an efficient way of doing things. One might wonder why we don't just take the absolute value of the residuals. I'll leave that to the big brains in statistics. All I know is that squaring is just as effective at producing the best line, and that's what we do in AP Stat. So let's talk about how we build this regression line using the correlation coefficient. This is where we learn what the correlation coefficient R actually is. So recall that the correlation R, our correlation coefficient, is the measurement of the strength and direction of the association between variables. And also that a z-score tells us how many standard deviations a data point is from the mean. That is what a standard score or z-score is. When we standardize data, we say how many standard deviations a data point is from the mean. We're going to have to keep those two concepts in mind. So to understand how we get the least squares regression line, the LSRL, what we first need to do is standardize the x and y values of each data point. So we're going to take all of our data points, take their x and y values, consider all of the x values, all the y values, and standardize the x and y values for each point. So we're going to assign standardized x and y values for each point. Essentially, we're going to give each point z-scores. Okay, we're standardizing our data. The graph of the standardized data points for the roller coasters is below. So we took every bit of roller coaster data and we standardized the x values, standardized the y values, and plotted the new point over here. And you see there's a line of best fit that goes through those standardized data points. Wonder what that has to do with the actual regression line. So R tells us that if we were to move one standard deviation away from the mean x variable value, now mind you, in standardized data, the mean is 0, okay? So if I were to move one standard deviation away from the mean x variable value, what part of a standard deviation would I expect to move away from the mean y variable value? Okay? So we see in this graph right here, if I move one standard deviation to the right, I move r standard deviations up. And when I move horizontally, I move according to a standard deviation of my x values. And when I move up, I move r number of standard deviations for my y values. Okay? So, in other words, that means for every one standard deviation I move in the x direction, I can expect to move about r standard deviations in the y direction. It looks like a little rise over run is happening here. And the math term that comes to mind is slope. So, for our standardized data, r is the slope of the least squares regression line. That is what r actually is. It is the line of best fit through our set of data if we were to standardize each and every one of those points. Okay? And we can write the equation of that line of best fit in this way. Okay? So we have z standardized speeds, and this little hat here, z hat, means we are predicting speeds, okay? And we do that by saying, well, I have my standardized heights over here, and for every one standard deviation I increase in height, I increase in speed by 0.814 standard deviations. So I take my standardized height, multiply by my value for r, which we saw earlier in the lesson is 0.814, and I get an approximation what my line of best fit says my standardized speed would be. How many standard deviations above or below the mean speed I can expect to be. So I'll be the first to admit this content is quite heady. Feel free to go back in the video if you want to review any details. But we are just setting the table, as it were, for some early applications in regression analysis that we're going to be doing, analyzing lines of best fit that we're going to be doing. This is about as heady as it gets for this section. Once we get to the applications, they're actually not that bad. So, just to finish setting the table, you'll also remember that r is between -1 and 1. -1 being the answer marching one by one down and to the right. 1 meaning the answer marching one by one up and to the right. So in this context, that means that relative to the standardized x values, the standardized y hat values regress to the mean, hence regression, okay? R is almost always between -1 and 1. The ants are not, in real-world data, ever going to be marching one by one down and to the right or marching one by one up and to the right. So this is why we call it a regression line, because this value r describes the nature of the regression, okay? We say for every change of one standard deviation of height, we don't increase by one standard deviation of speed. At least that's not what our line of best fit predicts. We only increase 0.814 standard deviations of speed. All right, there's a bit of regression back to the x-axis, if you will. All right, one standard deviation change here does not mean one standard deviation change there. There's a little bit of regression. So for our example, our regression of 0.814 means that for every one standard deviation increase of height, as I said, We don't expect to increase a full standard deviation increase in speed, right? The speed regresses back to 0.814, and that is why we call this the least squares regression line. So now we're going to solve some problems using that idea of regression, that idea of R being a slope of a line of best fit for standardized data, okay? So these problems are 3 of many problems related to this description right here. So let's read it. A scatter plot of house price in dollars versus house size in square feet for houses sold recently in Saratoga, New York, shows a relationship that is straight, so got a linear relationship, with only moderate scatter and no outliers. So our data are conducive to a linear model. The correlation between the house price and size is 0.76. That's R, okay? The least squares line is thus and such. We're actually not going to use this least squares line. We're just going to be using R, okay? So you go to an open house and you find that the house is 1 standard deviation above the mean size. Note, our units for house size here are actually not square feet. They're standard deviations, and that tells me I'm working with standardized data. How many standard deviations above the mean price would you predict it to cost? Okay. Now we may be tempted to say, ooh, the size is 1 standard deviation above the mean, so wouldn't the price be 1 standard deviation above the mean? Nope, that's not what our equation says. Our equation says that if I input a standardized x value, I multiply by R to get my standardized y values prediction, okay? So how many standard deviations above or below the mean y value I can expect to be. So if I were to be 1 standard deviation above the mean size, I would be 1 times R standard deviations above the mean price. So we would predict that we would be 1 times 0.76, which is 0.76 of course, standard deviations above the mean price. Okay, gotta be careful. Number 2, you read an ad for a house that's 2 standard deviations below the mean size. What would you guess about its price? Again, we cannot say 2 standard deviations below the mean size means we can take a guess that there's going to be about 2 standard deviations below the mean price. We need to acknowledge the reality of regression. For every 1 standard deviation below the mean, we are 0.76 standard deviations below our predicted price, okay? So we predict the price would be 2 for 2 standard deviations below the mean size times 0.76, my value for R, which is equal to 1.52, standard deviations below the mean price. So we take the number of standard deviations for my X variable, size, and we multiply it by R again, just like in number 1, and we get our estimated standard deviations below the mean price. Okay, number 3 is kind of a trick question. A friend tells you about a house whose size in square meters, he's European, we're using a metric system, is 1.5 standard deviations above the mean. What would you guess about its size in square feet? Implication, answer is in standard deviations, not dollar values. Think about it. Does changing a variable's units affect the z-scores of its values? Think about this, see if you know the answer, and then I'll reveal the answer. Okay, I'll assume we're ready to continue. Feel free to pause the video if you need some more time. The size in square feet is also 1.5 standard deviations above the mean size. Changing the units for a variable does not affect the z-scores of its values. If a house is 1.5 standard deviations above the mean in meters, and square meters that is, and I convert my units to square feet, well, I didn't change how many standard deviations that data point is away from the mean. So to finish things off for this lesson, we're going to solve some problems using R, but we're going to introduce some real units here. We're going to start to use units like US dollar for the house price and square feet or perhaps square meters for the size of the houses. All right, so this whole scenario is the same as before. R is the same as it was before. We'll use this line eventually, but let's go to number 4 here. Suppose the standard deviation of the house prices is $77,000, okay? So how much more expensive than the mean price would you predict for the house in part 1? And mind you, the house in part 1 is 1 standard deviation above the mean size, okay? So think about it. If I increase 1 standard deviation above the mean size, how does that affect my prediction for the price, okay? So if 1 standard deviation of price is $77,000, would I not take 0.76, my value for R, and multiply that by 77,000? Because if I increase 1 standard deviation above the mean size, I increase 0.76 standard deviations above the mean price. At least that's my prediction. That's what R means. Okay, that evens out to 58,520 above the mean price. So again, we're taking a standard deviation. Now we have real units. We have US dollar, and we multiply that by R, which accounts for the regression for my y-axis variable, my predicted prices. So number 5, suppose the mean price for all of these houses is $168,000. Oh, if only. Not these days, thanks to inflation and increased house prices all around. So what is the predicted price for the house in part 4 that's 1 standard deviation above the mean size? Okay, so similar idea to before for this one. See if you can do this one on your own. Pause the video and unpause the video when you think you have an answer. All right, let's check out that answer. We predict that the price would be, okay, so here is the mean price of the houses, and here is our predicted increase above the mean from part number 4, okay? We add those together. Here's my mean, here's my increase above the mean, and we would get that amount. That would be the price of a house whose square footage is 1 standard deviation above the mean size. Okay, so now we get to put one more piece in the puzzle. The mean size of the houses is 1,800 square feet, and the standard deviation is 660 square feet. We are going to predict the price of a 2,460 square foot house. I swear I can say numbers. That is 1 standard deviation above the mean using the least squares equation. Ooh, we finally get to use this in the original units. All right, we're using some real units here to verify that you get the same prediction as in part 5. So we finally get to use an aggression. No, it's not mad. A regression equation in real units. And here's how we do it. We are going to substitute 2,460. The mean size is 1,800. 1 standard deviation above is 660 above that, which evens out to 2,460. If we substitute this in for size and we do a little bit of arithmetic, we should get the same estimated price as we did for part 5. So you try it for yourself, substitute this in for size, plug and chug, and see if you get a similar predicted price. And in fact, we do. We predict the price would be 8,400 plus 88.67 times the number we substituted, which is 1 standard deviation above the mean house size of 1,800 square feet. And we get that, which is frighteningly close to that, okay? So that little discrepancy there is probably due to the fact that these values are rounded, okay? So it's not going to be perfect. But if we're only off by, what, $8.20, that's not bad. Definitely not.